Hello and welcome to week 3 of Algebra 2 Accelerated. I just want to give you a warning as we get started here. This lesson is a little longer than the last 2 weeks, and it's because we're covering some kind of complicated concepts. And also, since I don't have a bell that I have to adhere to, I'm just going to explain things lots of different ways and keep talking. Because why not? If you don't need this extra information, you can skip it, right? You have the ability to just skip ahead a little while until I move on to the next subject if you don't need extra explanation. But I just thought it was really cool that at least in this sense, we get to learn at our own pace. So I might go on and on about a few different explanations, but yeah, feel free to skip ahead if it's something that you understand and don't need the extra explanation. So yeah, like I was saying, we are on week 3, so that's why it's 8.3. 3 main concepts that we're going to go over, not necessarily in this order, is sample space, the idea of independent and dependent events in probability, and then also tree diagrams. So last week we talked about Venn diagrams, which is a way to draw a picture that helps you express probability. And this is a similar thing. It's not the same kind of probability that it helps you express, but it's also a very useful visual diagram. So another very cool, useful diagram to help us understand probability. And then our goal is to, basically learn about those 3 things. Tree diagrams can help us represent independent and dependent events, and that's why they're so helpful. Okay, so I want you to take a minute for the access, and there's a typo. It should say, what does the word independent mean to you, and what does the word dependent mean to you? Of course, there's typos because it's a Jarmic original. And just think about what they mean in real life to you, because that can really help us as we move forward to think about what do they mean specifically to probability in mathematics. Okay, so hopefully you had a few minutes to think about that, and we'll come back to that as when we go back over the independent and dependent events definition. The first thing I want to talk about, though, is single event probability, and that's what we've been doing so far. It's the idea that you have one event that happened, so you have, one coin that you flipped, one card from a deck of cards that you pulled, and picking one person from a group of people. We saw that in the Venn diagrams. Picking a marble from a bag of marbles, right? One marble, that's one event. And one thing to keep in mind is however many events you have, that's how many fractions you're going to have. So far we've been dealing with pretty much only one fraction so far for every probability. So let's just do a review. I'd like you to pause and review doing these student examples A, B, and C. And they should be reviewed from the last couple weeks and just give you a reminder of what we're doing. Okay, so hopefully you paused and tried those. I'm going to go through them step by step just because, like I said, if you don't need this extra help, skip ahead, look at the answers I got, make sure you got them right, keep going. If you do need a little extra help on the last couple weeks, maybe follow along with me. Okay, so here we have a spinner, right? You spun the fair spinner, and that just means that it's equal. It's equally likely you'll get in any spot. And here we need to find the probabilities. Okay, so A, what's the probability that you get blue? Well, there's 1, 2, 3 out of 8, so it's just 3 out of 8, which is 37.5%, I believe. 37.5%. All right, and then for B, we have what's the probability that it's even intersection blue? So that means that it has to be where they overlap, right? This was very helpful for Venn diagrams where you can see the two things overlap. But also in week 1, we talked about where do these things overlap as well. So we can say even is 2, 4, 6, and 8. And then blue is these 3. So where they overlap is 6 and 4. So it's only 2 out of 8, or 25% chance that you will land on something that is both even and blue. Now, the difference between that, and hopefully this is something that we are comfortable with at this point, even union blue, that is everything that's blue and everything that's even. So everything we just highlighted, right? Not just the overlap, but everything we just highlighted is a part of that. So it's 8, 2, 4, 5, and 6. So we have 5. Come on, 5 out of 8. And as a percent, that is 62.5%. Okay, so hopefully that was a review for you. Take a second and get your calculator ready. If you have a calculator, actual calculator, that's great, especially one that has a fraction button on it. We're going to be using the fraction button. Otherwise, hopefully you have this calculator that looks like a little equal sign. I'm going to clear this out because we want to be able to use the fraction button on these. And let's see, you guys get to watch me try and be sneaky here and learn how to do all the iPad tricks that you guys are good at and I'm not that good at yet. Okay, no, there we go. Yay, I did it. So I know you guys are much better at this kind of stuff than I am, but I just wanted to make sure that we're going to be using the fraction button. And so you want to press the over, which is down on the bottom by the infinity word, that little over button. And then that shows you that you can put a fraction in, and that's going to be really helpful. All right, so let's take a look at this next definition. And I want this to be like, there we go. Crushing it. Technology maven. Reporting for duty. Okay, so we have multiple event probability. And hopefully some of you have seen these rules before. But if not, here's your review. It's called the multiplication rule of probability. And what it means is that if you have probability that's happening in a row, then it's something that's happening and then it's followed by another event. So something happens first and then something happens second. And then you multiply the probabilities together. So, you multiply the probability of the first thing times the probability of the second thing happening. And same, it keeps going. So if there's 3 events that happen, it's the first probability times the second probability times the third probability. Okay, 5 things, 5 fractions. And so that's why it's important that we know how to use our calculator with fractions. Okay, so let's do a few teacher examples, and hopefully this will help us to understand. We're going to spin this spinner, same problem, except for you're going to spin it twice. So whenever you're doing a problem, you notice that something happens 2 times in a row, 3 times in a row, 4 times in a row. That's how many fractions you're going to have. And you just want to set up your fractions right away. Okay, so what are the following probabilities? So what's the probability that you get blue and then blue? So I just want to note that you might see this as probability blue, blue, like that. And you also might see this written as probability blue, comma, blue. Both of those are common ways to note that things are happening in a row. Okay, so the probability that you get a blue, we did that before, right? It's 3 out of 8, so 3 out of 8. And then it's multiplied times the probability that it's blue again. And something to be aware of when we're dealing with the spinner is the probability is the same, right? The spinner stays the same from the first to the second to the third to the fourth, however many spins you're doing. So the probability that you get a blue and then again you do the same probability, you get another blue, right? It's less likely that you would do something twice in a row. And so that's why we multiply, because when you multiply something that's smaller than 1 times something that's smaller than 1, then you get a smaller number. So here is our percentage. Remember, you just multiply by 100 to get a percent. And we're going to round it. If I don't tell you how to round, which I will always try to remind you how to round it to the 100th place after you turn it into a percent. Okay, so let's take this and keep going. Let's do question B. This one says, what's the probability that we get an even intersection blue? So let's start there. Even intersection blue is going to be our first fraction. And then just plain blue. So we have 2 things happening in a row, so we need 2 fractions. Now we already did this problem above. Even intersection blue is going to be 2 out of 8. And then blue is 3 out of 8. We just did that a couple times. And so we are just going to change the fraction. So all I did was press up. That way I don't have to deal with redoing everything. I can just change this to be a 2. Little time saver. All right, and then I know that's 9.38% if I'm rounding it correctly. So the probability that you go and you get either a 6 or a 4, because those are the 2 that are both blue and even, and then you spin it again, you get a blue, it's about 10% chance that that'll happen. You know, not a very good chance that you'll get 2 things that you want to get in a row. Okay, so let's do the final one. It says even union blue and then even intersection blue. So we have 2 things happening in a row. So again, I like to set up my events. The first one is even union blue. We did that above. That was 5 out of 8. And then union intersection blue, again, we just did that. So that's the 2 out of 8. And then our calculator trick is to go back and just delete one of these things or both of these things so I don't have to redo the whole thing. That's a 2 out of 8. All right, so we have 15.63 is our correctly rounded answer. All right, so I want you to pause the video and try the A, B, and C student examples. Remember, really, if you're not pausing and trying them on your own, then you're missing out on a really big chunk of the best way to learn math. The best way to learn math is to try something, make a mistake, see where your mistake was, try again. Maybe you're gonna have to repeat that process a few more times, but if you just watch somebody do math correctly over and over, you're not really going to learn how to do it, because even though you've seen it done perfectly many, many times, you're not sure how to do it perfectly. And that's okay. Hey, distance learning, right? This is the perfect spot to make mistakes and try things because nobody's watching you. You're by yourself. You can make mistakes and then you can just laugh at yourself. You don't have to worry about anybody else seeing it. Okay, so pause the video. And hopefully you're back from trying the problems. I'm going to go through them. So the first student example says red, then red. Well, that's 2 events, right? Red, red. And then it's the same spinner, so as the same denominator, that's the same. And there's only 1 red part in the spinner. So it's just 1 out of 8 times 1 out of 8. I'm just going to go back into my fraction that I have set up, and I'm going to, if I can get it to work, there we go. Change it to 1 out of 8, 1 out of 8. And I get 1.56% if I'm rounding it correctly, which makes sense, right? It's not very likely that you're going to spin the spinner, get it on a red, and then spin it again and get a red again. Very unlikely that that happens twice in a row or even once in a row. Once in a row? One time. There we go. Okay, let's try B. It says odd intersection red and then a red. Okay, well, two events, and this one's kind of meant to be a little bit of a trick for you. Odd intersection red, that is just 1 out of 8, right? There's only one number inside of the red, and look at that, it's odd. So it's 1 out of 8. And then red again, that's just 1 out of 8 also. So this one's a little bit of a trick question to make you think, but it's 1.56% as well. All right, let's look at the final question here. The final question is odd union red, then odd intersection red. So odd union red means we have red and then we have all the odd numbers. So that's a total of 4 out of 8 possibilities. And then our second roll is odd intersection red. We just did that. That's 1 out of 8. And so if we were to, change this one to a 4, and actually remember that when you're multiplying, it doesn't matter what order you're multiplying in because multiplication is communicative. So you could just, you could multiply the 1 out of 8 first and the 4 out of 8 second. Doesn't really matter, but when we're still learning this, it's best to set it up the exact same way. 6.25% is the answer there. Okay, so this was my introduction to the concept of multiple events. The big idea I want you to have in your head right now is that if I were to spin the wheel 3 times, I'd have to multiply by another one. If I multiply the wheel, or if I spin the wheel 4 times, I would have 4 fractions being multiplied, right? So that's the main thing I want us to move forward with, is the understanding that every time you have another event, you multiply by another fraction. Let's take a look here at the different kinds of things that can happen in a row. The first thing is what we've been looking at so far, and this is where your understanding of independent, the word independent, comes into play. Because when we think of independent in terms of being an independent person, maybe we think about paying our own bills, and we think about living alone bai, or we think about somebody who is has independently minded or something like that. But I think when we're talking about it in terms of mathematics, it's a slightly different understanding. So it's an outcome, so something that happens, an event that happens that is not affected by a previous outcome. So it doesn't change based on what happened before. So you could say if you were planning an outdoor party, right, and it started raining, if you did not change any of your plans based on the fact that it was raining, you would be independent. Kind of a different understanding than what we have in real life, right? If somebody was talking trash about you and you didn't let it affect you at all, you would be independent. The not letting it affect you is independent of what the other person did. So independence in our mathematical world is slightly different than independence when we think about paying your own bills, being alone, living alone, those kinds of concepts. So what kind of things happen in probability land that are independent? And probability land is sometimes a little bit different than real life. You could always come up with a scenario where for a spinner, the more you spin it, the more run down it gets, so the probabilities change. We just assume that maintenance doesn't need to be done on our objects and that things stay the same. So yeah, probability land, we kind of get rid of that disbelief and just kind of assume things are in the perfect world. So a coin flip is an example of that as well. So when you flip a coin, it lands on head. If you flip it again, it has the same probability of landing on a head or a tail, right? It didn't change. And we don't talk about it landing on the side, or, if you flip it and it lands in a piece of gum and that side's stickier or something. We don't consider that. We just say it's a 50-50 chance. It stays the same no matter how many times you flip the coin. So that would be those would be independent events. Let's talk about wheels. Wheels are the same as spinners, so don't worry about that. Dice. So dice just means more than one die. And you might see the word number cube used also for this. But basically, if you roll a die, it doesn't change if you roll another die. And then we're going to see some examples of something called with replacement. So that means when you're putting an object back. So if you have a bag of marbles and you pull a marble out, you put the marble back in and shake up the bag again, it's as if you never took the marble out, right? And we'll see an example of without replacement in a minute. That does matter. Okay, and then anytime you see a probability where it's given as a percent, we consider that to be independent at all. So let's talk about why just a little bit. The reason is because percent doesn't actually mean you have 100 items, right? If I said I have a 90% chance of being on time, it doesn't mean that I went and tested it 100 times and 90 out of the 100 times I was on time, right? It means that I have averaged a scenario. And so I don't actually have objects. I just have a concept of the ratio of how many times something happens or doesn't happen. So that's why we don't consider it to be dependent. Although in pre-calc, you might see some situations where it is dependent. For us, we're just saying if it's a percent, it's independent because it's an average and it doesn't change. Okay, so if you want to try to think about it, go ahead and try it. I'm going to skip over it for now, but feel free to email me if you have questions about the think about it, you feel like challenging yourself. I just know this video is going to be very long, and so I just want to make sure that I'm not stopping at every little part. Okay. Let's keep going. We're going to talk about the definition of dependent, right? And so maybe when you were thinking about the word dependent in your life, it meant that you needed help from somebody, or like you're a young child, so you are dependent. When we talk about taxes, you can talk about somebody being your dependent means that you have to pay for them. And so then you get taxes off because you had to pay for another person. Again, in probability land, the meaning is a little different. The meaning of dependent is an outcome that is affected by a previous outcome. So the example that I gave where you're deciding to have a party outdoors, right? If it starts raining and you decide to change your plans, that means you would be a dependent, right? You would be your probability is dependent on what happened before. And if somebody's talking trash about you and it did affect you, then that would be something that you are dependent on that event. How you feel depends on what happened before you. And so here are some examples that you're going to see in probability questions that we're going to go through. And it's really helpful to just kind of memorize what is independent and what is dependent when you're looking at problems about probability. So let's talk about this. It says picking two different people. Picking two different people. Now, different people is the key. So if I had a class and I was trying to pick people to present, right? I could pick somebody to go first. And then I would want to pick someone different to go second, right? You wouldn't want to hear the same person give the presentation twice. You would want to say, okay, first person goes first. That person is now removed from the class. Therefore, the probability changes in the classroom. I'm removing someone from the pool that I picked from second. And so that's why it is a dependent situation. Who you pick first changes the probability of who you pick second. So let's take a look here. I think this one is the most clear visual example that I can do. It says picking two different marbles. Okay, so we've seen bags of marbles quite a bit so far. So hopefully this is not something that's going to throw you off too much. We have just kind of a little cartoon of a bag. And then let's do like a few green marbles in there. Those are not very clear. Let's make these a little better here. Okay, a few green marbles, boom, boom, boom. And then let's do a few purple marbles. That's 3 green and 4 purple marbles. So let's say I'm picking 2 different marbles. So I could pick one marble. Let's say I reach in. Here's my first fraction. What's the probability that I get 2 purples in a row? Let's say that's what we're trying to figure out. Well, the probability that you get a purple on the first pull is 4 out of 7, right? So 4 out of 7. Now I need to pick a different marble. I can't pick that same marble again. I'm taking it out and I'm not putting it back in. So here's my purple marble oops. My purple marble got kicked out. It is no longer inside of the bag. So now when I go to pull a purple marble again, I only have 3 to pick from out of a total of 6. So dependent means that your fraction is going to change for your second item that you're picking. And it's always gonna change the denominator by 1. So again, if I said, okay, actually I wanted to find the probability that I get a purple marble a third time. Well, let's say I got that marble the second time. Now that marble is also gone. I need to pick a third different purple marble. So that would be 2. And then there's only 5 things left in the bag. So when we're dealing with dependent probabilities, the denominator is always going to go down by 1. And depending on what you're asking, the numerator might go down by 1 or it might be a little bit different. Okay, so let's move on to more of these definitions. We have anything without replacement. So if you see the word without replacement, it means the same thing as picking different items. It basically means you're taking it out of the bag and then you're not putting it back in. Oh, stop. Sorry, my cat is attacking my table here. You're not putting an object back is what it means. So another way to say this too is that you're picking something at the same time. Well, you can't pick 2 of the same thing at the same time. You have to pick 2 different marbles in order to take them at the same time. And this can be confusing because we think of something that happens at the same time as being one event. But since you have to pick 2 objects or 3 objects or 4 objects, that means there's 4 events. 4 things are happening, even though it says at the same time. A little confusing, right? Okay, so here we have a ton of scenarios. What I want you to do is read through them and decide if they are independent or dependent. And then I'm going to go through one by one and kind of explain each one. Again, pause, do these on your own, come back. You don't have to listen to me go through every single example one by one. You could skip ahead until you can see all the answers, check your answers. If you get a bunch wrong, go back and listen to me go through them. If you don't need the extra instruction, you don't have to listen to me if you don't want to. It's up to you. This is just extra explanation because we have extra time, because we don't have to go by a bell schedule right now. Okay, I'm going to go through them. We have selecting a marble and then choosing a second marble without replacing the first marble. So hopefully this without replacing, that's the key word. It means that you're changing the bag of marbles from the first to the second event. And so this is dependent. Another way to remember this is dependent, different, denominator. Dependent, different, denominator. So it changes the denominator. Selecting 3 different marbles. Dependent, because you cannot pick the same marble over and again. You have to take that marble out and set it aside to make sure that you don't pick it. And that means that you're changing what your bag of marble looks like. So that changes your denominator and it changes it. So it's dependent situation. Dependent, different, denominator. Okay, selecting 4 marbles, replacing the marble after each selection. So that would be independent, because if you take something out and then you put it back in, you shake it up, you have the same exact bag of marbles that you started with at the beginning. So it's independent. It does not change the denominator from pick to pick to pick to pick. Selecting 3 marbles at once, that would be dependent. So dependent because you cannot pick the same marble 3 at once, right? You need to have 3 marbles in your hand. You can't have the same marble 3 times. You only have one of them. You have to pick 3 different marbles. So basically you're taking it's the same exact question as question B, but just worded a little differently. Okay, rolling a number cube. Again, that means the same thing as die. And then spinning a spinner. Or you could have them happen at the same time. So this might be a little bit confusing because there's 2 totally different things happening, right? You're rolling a die over here and you're spinning a spinner over here. But the way to break it down in your head to make sure that it makes sense is that if you roll a die, does it change anything about this spinner over here? No, absolutely not. So this would be independent. Okay, drawing a card from a deck of cards. And I actually have a deck of cards here that I can kind of hold just as a little explanation here. We don't want jokers. We want 52 cards, not 54. Okay, so you are drawing a card. Pretty good at shuffling. I don't know if you guys can see, but so let's say I have a deck of cards and I picked a card at random, got the 5 of hearts, and it says, I took it out, right? And then it says replacing it. So I'm going to put it back into the deck of cards. And then I'm going to shuffle again, right? So my deck of cards is exactly the same as it was before. I took the card out, but then I put it back in. I replaced it. And so now my probability starts over again. I have a full deck of cards. Everything's the same. So that one would be independent right there. Replacing it is the key word. This one has a %, so we're automatically saying independent. So the idea is that when you shoot a free throw basket, you know your player's free throw average usually. And so you would just say, okay, well, the 2 shots do not change. The first shot does not change the probability of the second shot. In real life, it might, but whenever you're given a %, just assume it's independent. A teacher will be picking 2 different students to make a presentation. We already talked about this one. This one is dependent because we have to have different students, so the denominator is going to change. Okay, so I was just thinking about this next one. When you are listening to like Pandora or Spotify or YouTube and they pick the next song that you want to listen to, I don't know that like one song, like if you're listening to a song, that song does not change whether or not you're going to like the next song. So I thought of this as being independent. If you have an argument that it should be dependent, let me hear it. Shoot me an email. Let me know what you think. Okay, pulling 2 prizes from a prize bag at the same time. So you need to pick 2 things at the same time. Automatically, they need to be different. So different, denominator, dependent. Picking an appetizer, an entree, and a dessert from a menu. Now, this one we could argue either way in real life. Like if you picked a really big appetizer, maybe you'd pick a smaller entree, something like that. So in real life, I would say this would be dependent, but for probability problems, we say it's independent. The first choice is for an appetizer. That's separate than the choice for an entree. And there's nothing to keep you from ordering whichever appetizer with whichever entree with whichever dessert you want to order at a restaurant. So we would consider that to be independent. And then finally, you need to select a team of 4 people to play volleyball from a group of 20 people. That's dependent because you need 4 different people, right? You can't pick the same person. You need 4 different people to be playing on your team so you can have 4 different positions, right? And so they need to be 4 different people. So what I'd like you to do, just to end this little part of the lesson before we move on to tree diagrams, which can help us think more logically about the independent and dependent probability is come up with your own independent and dependent events from your real life, and feel free to like look around the room and think about picking things, or the last time you heard something about a percent chance that something could happen, and then think about that happening twice in a row. It's good to relate it back to your real life. So go ahead and pause and try to come up with a dependent and an independent situation from your real life. All right. So now would be a really good time to take a break if you need to take a break. Pause, get a drink of water, use the restroom, whatever you need to do. Make sure that you are ready to go, because we're going to launch into something that might take a little while. Again, if you don't need all this extra explanation from me, feel free to skip ahead and just check your answers. Also, this PDF that I'm creating right now is available on Schoology. So you could just try these problems on your own and then look on Schoology, the PDF on Schoology, to check your answers and not have to listen to the whole video too. So keep that in mind. I do encourage you, though, to make sure that you're trying every question and that you're checking your answers as you go. All right, so we're going to talk about tree diagrams now. And tree diagrams help us figure out how many possible ways something could happen, multiple events could happen, and it also helps us visualize independent versus dependent events and probabilities. So here we have our scenario. A coin is flipped twice. Pretty simple, right? Just flipping a coin twice. Whether it lands on heads or tails is recorded. And we're going to create a tree diagram for this scenario that shows all the things that could possibly happen, all the possible outcomes. So the first thing we need to talk about is step 1 here, and I've broken it down into steps. Again, this is me just like giving you a really good framework for how to do this. If you want to do it differently, you can. This way is just the best way that I found from teaching this year after year. Is this an independent or a dependent scenario? It is independent. Your coin does not change if you flip it from first to second. Just because you got ahead on the first flip doesn't mean you couldn't get ahead again on the second flip. So how many events are happening? We're flipping the coin twice. That means there are 2 events in a row happening. And then how many options are there for each event? There's 2 options, right? Heads or tails. So let's set up our tree diagram. The first thing you want to look at is your number of events. So we are going to make the events happen in a row from left to right on our page. So event 1, I'm just going to label 2 spots, left to right. Event 1 happens, and then event 2 happens. Now we're going to think about how many options are there for each event. And this is what I call the branches on the tree. You have 2 options for what could happen. You have heads or tails. So these are your 2 options. So there's only 2 branches on each fork. Now you're doing this twice. And so every outcome you have here, you need to consider that same thing happens a second time. And the nice thing about doing this on the iPad is that as you move stuff around, it's easy to copy and paste, and that makes it so you don't have to do so much writing. And then here we go. There's our tree diagram. So you have the first event, you could get a heads or a tails, and then after that, you could get a heads or a tails again. So it's independent and nothing changes. Label the branches with the probabilities. Now this one is the most simple probability. They're going to get much more complicated than this, but it's half and half for every single branch on the tree. Notice how I labeled the end of the branch with what happened, and I labeled the middle of the branch with the probability. That is the format that you should be following for this. So the end of the branch tells you what's happening. You don't have to write the whole word, you can abbreviate it. And then the thing in the middle is the probability of getting there. All right, and then this part, I want you to do, at least with me on this first one, it does get a little tedious and it does get to be a little extra work after a while, but I just want you to be able to see how it works to label all the branches. So the end of this branch represents the probability that you flip the coin, lands on heads, flip it again, lands on heads again. So probability of H, H. That's one way. You could put H then H if you wanted to, but I like to save room and save handwriting. Okay, so what's the probability of that happening? Well, we know it's 2 events, so it's 2 fractions, and we're going to write the 2 fractions 1/2 and 1/2. That's this and this being multiplied. So that's why tree diagrams are such a nice representation, visual representation of what's happening, because you're following a path and it tells you what your probability is going to be. And now I'm going to move this over a little bit, and this probability is going to be 25%. 1/2 times 1/2 is 1/4, which is 25%. And you can do that on your calculator if you don't trust me. Now, this next one is the probability that you get heads first and then tails second. This is the exact same scenario, except for you're doing 1/2 from this first fraction times 1/2 times the second fraction, because you took a turn. You didn't go H, H, you went H to T. So you have 1/2 times 1/2 equals 25%. Now, like I said, this is the most simple scenario. It's the one where everything is all the same. Not all of our scenarios that we run into are going to be like this. Some of them are going to have all different outcomes. You're going to have different probabilities on each branch. So started with something very simple, but it does get a lot more complicated. So that one represents, this 1/2 times this 1/2. And then finally, probability of tails twice in a row is this 1/2 times this 1/2, which is 1/2 times 1/2, which is 25%. Okay, like I said, going through and doing all of these probabilities, not entirely necessary for every single problem. It's just good to do it at first because, most importantly, it shows that if these are all the things that could possibly happen, you know that all of these probabilities need to add up to 100%. Or if you're giving a probability as a decimal, it would add up to 1, right? 100%, 1 means the same thing. So that's a good way to check that you set up your tree diagram correctly, is to find all the probabilities at the end of the outcome and add them together, make sure you got 100%. Quick vocabulary, and it's something that every single time I give a quiz or a test, somebody comes up to me in the middle of the quiz or the test and says, "What is this question asking? What the heck is sample space? What are you talking about?" This is one of those things where it's a piece of vocabulary and you need to memorize this term sample space. And then you need to memorize that it means listing all the possible outcomes. So all outcomes. And there's a really specific way that you have to list them, because fancy, old dead white guys decided that's the way that you do it. And we're going to have our pinkies up and we're going to use the right fork and we're going to be very polite and we're going to do it the way that they want to. So the sample space is S equals, then you draw a little, what I call a mustache bracket, but it's called a curly bracket, and you list your outcomes. Now, how are you supposed to list them? This right here is one outcome. Then you separate it with a comma. So this next part is the next outcome, heads then tails, and so on. Tails then heads, tails, then tails, and then you close it with a curly bracket. That's it. It's just a silly little thing that, you just need to know the definition for. Excuse me. And you need to know how to approach it. I have a sip of my coffee here. Okay. So now let's actually answer the questions that are being asked. The first question is, what's the probability that the coin lands on heads both times? So if we didn't already do this problem, we need to set it up. Now, this might seem silly for this question because it's such a simple question, but something that I do that really helps me keep track of what the question is asking, it says lands on heads both times. So underneath, I'll do a little label and I'll say, okay, I know that means it needs to be H the first time and H the second time. And I know the probability of H is 1/2 and then 1/2, which is 25%. Looking up here, we can see that this probability is that same probability here. We can see that it is probability of HH. Okay, so go through these next ones a little faster. Hopefully you can see the pattern that's emerging. The first coin lands on, well, we have two situations. And then we say the first one lands on heads, but the second one does not. So that would be the same thing as saying tails. And because there's only two options, right? It's either heads or not heads, which is tails. And we know that all the probabilities are the same in this scenario, and it's 25%. If we wanted to make a connection to our tree diagram, we know that this represents this second probability here, HT. All right, first is tails, second is not tails. So tails, and then you're gonna see me use this notation NT or N whatever it is. So up here, I might have wrote NH instead of just T. And basically what it reminds me of is that it's the opposite of T, the opposite, whatever is left over to 100% from T. But we'll talk about that a little bit more later. So this is 1/2, and then not tails is heads, so it's 1/2, and that's 25%. And again, if we wanted to connect this back to our tree diagram, we would see that this 25% is there. And then finally, the coin lands on tails both times. We have tails, tails, that's 1/2 times 1/2, and that would be 25% as well. And that corresponds to the final part of our tree diagram. Okay, so go ahead on to the next scenario. The next scenario is, as you can see, it's flipped 3 times. And I really want you to try and draw your tree diagram without peeking at what I did first, because I think that can really help you understand how this works. So go ahead and pause the video, try the next tree diagram on your own, and then I will reveal the answer and go over a couple little tricky spots. Okay, so let's see what it looks like. You can see here, the main thing that I noticed the most that students make mistakes on is that they get confused that there are 2 choices, but there are 3 layers of those 2 choices, right? And some students get confused. They might go, okay, this is my first, my second, my third event. And then they go, okay, then it's HT, then it's HT. No. Each event gets its own column and each choice gets its own branch. So make sure that you did your tree diagram correctly on this. And you'll notice, again, we are dealing with the most simplistic scenario for probability, 50-50 chance of something happening. And so these are all the same. They're also half as much of what they were last time, which kind of makes sense because you're just adding another coin flip. Here is our sample space. And here I wrote out the probabilities, but they also correspond to some of the things that are in the tree diagram. Remember, you're going to start seeing me once things get a little bit more complicated. I might write not this, instead of saying tails, tails. And then it says, and that was the only one that says do not. So just keep that in mind. You might see me start using that NH instead of saying tails, because not all scenarios have two choices. Some of them have more than that. Okay, let's see a scenario that has more than that. Okay, so we have two of our classmates in this question, Naomi and Isabella, and they were talking about career choices is what I decided they were talking about. They were talking about becoming a DNR officer, which is like a police officer in the forest, basically, a firefighter, or working as an EMT. All very important jobs, really cool choices. And that reminds me, we're going to stop right there. Is this an independent? Oh, wait, no, let's keep reading a little bit more. It says, they decided that there's a 45% chance of becoming a DNR officer, 35% chance of being a firefighter, and the rest is EMT. So 45 and 35, 45% plus 35%, that's going to be 80%, right? So let me make sure, because I make mistakes all the time. Yep. And so when that says the rest percent is the chance that they become an EMT, they're talking about up to 100%. There's only 3 choices. So we would say the rest is a 20% probability. Okay, so we were just talking about if you see a percent, right, you just know it's independent. So you know this is an independent situation, which means that every single fork that you create is going to be the same as you go to event, to event, to event, to event. And how many events are there? Well, this one's a little tricky, but it's actually 2 events, because you have Naomi and you have Isabella, and each person needs to make their own choice about what they want to do for their career. And then how many options are there? Well, there's 3 career options that they're talking about right now. Okay, so we're going to set up the tree diagram. There's 1 event here, and there's 2 events here. Now, the branches on the tree are going to look a little different. And this is why I love, again, the iPads are really great for drawing tree diagrams, because you can make them, you can just copy and paste. You don't actually have to do all this by hand. So I'm going to make it pretty wide here. Our first career option that they were talking about is the DNR officer. And then they said firefighter and then EMT. Now, this is going to really help you when you're finding your probabilities. When you're given a percent, I could write my percent as a fraction. So I could say that this is 45 out of 100. And I could say that this is 35 out of 100. And then I could say that this is 20 out of 100. But then that means that you have to put in, like in your calculator, you're going to have to put in 45 out of 100 for your fractions every single time. And that gets annoying. So whenever you have a percent, my advice for you is don't use fractions for your percents. Unless you really like it and you want to just keep using the fractions, you can, but this saves you some time. You just write your percent as a decimal. And that's going to save you some time. You can just put in 0.45 instead of having to put in 45 over 100. Pro tip. Okay, so now all we have to do is copy and paste. And I'm going to make this a little bit smaller just because I've been around the block a couple times. I kind of know how much space I need. But, you know, if you run into a scenario where you're running out of space, something that I do often is make the tree diagram, the branches, smaller. Like this at first. And then I can make it bigger again, like that. So notice we have 2 columns, but every single branch has 3 branches on it, right? Every single event has 3 options. And so hopefully you did not do 2 people and then 3 off of each. Each branch should have the same number of branches on it. Each event should have the same number of branches on it. Okay, so we set up the tree diagram. We're done with step 4. We already labeled the branches with the probabilities because it's independent. We can just assume it's the same for every single one. Finally, label the end results with the whole path. Now, you can, right? Feel free. Go through, find every single one. P, D, D, that would be 0.45 times, running out of space here. Move everything over. There we go. Times 0.45. So 0.45 times 0.45. See how much easier that is than having to do 45 over 100 times 45 over 100? You're welcome. And that's 20.25, 20.25% is our final answer. Again, feel free to go through. The thing that is different about this one is that you have different probabilities, right? Everything was 0.5 or 1/2 before. Here, you are changing your percentages. So it's 0.35 for the second one. And we get 0.45 times 0.35, and that is 15.75%. Okay, I'm going to stop there. In the next example, I do have the answers all written out for you, so you can reference the tree diagram, but I think it's important that we go through the questions without all the answers, so we learn another strategy it's not as time consuming. Let's look at the first question. The first question says, what's the probability that both Naomi and Isabella become DNR officers? So that's 2 fractions because 2 people are making a decision. And we want to know what's the probability that the first one becomes a DNR and the second one becomes a DNR. Looking up at our scenario, we have 0.45 times 0.55. That's this times this, right? We already did this one. Now, I know I said fraction times a fraction, but here's what we're going to do when we're dealing with percents so that we save a little bit of time. I like to set it up like this, where it's no longer a fraction. It is now a decimal times a decimal. And we already did this one. It was 20.25%. So hopefully that one makes sense to you. So let's talk about this one. This is the what I was talking about where it's something happens and then it doesn't happen. So it says, what's the probability that Isabella becomes a DNR officer? Or sorry, this should say Naomi becomes a DNR officer, but Isabella does not. So it's DNR for the first one, but then it's not DNR for the second one. And I could go through all of these scenarios and add up all the ones where it's not a DNR officer. However, does not just mean subtract from 100, right? It's like the probability of D prime when we were talking about Venn diagrams or spinners. Probability of something not happening is just 1 minus the probability that it does happen. Or we could say it's 100% minus 45%. And so this would be not D or D prime would be, this one's 45%, we know that, and then this one is 55%. So we would just want to change this to 55, and we get 24.75. So our answer here is going to be 24.75%. Cool. Let's keep going. What is the probability that Naomi becomes a firefighter, but Isabella becomes an EMT? So this is firefighter multiplied by EMT. Fairly simple one. Firefighter was 0.35 and EMT was 0.20. So 0.35 times 0.2 is 7%. Kind of a nice round answer. I always like those. Okay, the probability that Naomi becomes a firefighter, but that Isabella does not, so that would be not firefighter. So we have to do the same thing again. Firefighter is 0.35. And then does not firefighter would be 1 minus 0.35, which would be 0.65. Let's go up here and change these numbers. 0.35 times 0.65, 22.75. All right, let's make some room for this answer. 22.75% is the answer to that question. Okay, so the next question is the same question, but again, it's adding another layer to it. It's the same exact scenario, but I changed all the numbers. So the only thing you need to be aware of as you're reading through is that these numbers have changed. So that means that the numbers on your tree diagram are going to change. So please pause, try to do the next one on your own, and then check your answer. All right, so hopefully you were able to try these. Again, doing all this, you don't have to do all this. It's just a strategy that can help you find the answers if you need that extra security of having every single situation laid out for you. And then here are the answers to your questions. So go ahead and check your answers there. Okay, this next one that I'm going to go through is probably the most important one that I'm going to do in the entire lesson right now. This next question, not only is it about my best friend, but it's also the most tricky. And that's because we are going to be dealing with a dependent situation. So let's take a look. We have Miss Mund is picking 2 Dare to Be Real students. Oh, that should say D2. We changed the name to be D2. Anyway, to take her field trip supplies on the bus to Washburn High School. She has 25 students to pick from, but only 19 of them are strong enough to carry the supplies. So what is happening here? We have a dependent situation because you need 2 people to carry the supplies. You can't pick the same person twice. You need 2 different people at the same time to be able to carry the supplies. So how many events are there? You need to pick 2 people to carry, right? So you're picking 2 people, so there's 2 events. So we're going to have column 1 and column 2. How many options are there for each event? Well, you might get a little confused because there's 25 students to pick from, right? But what do we care about? All we care about is if they're strong enough or not strong enough. So we're going to say there's only 2 options for each event. Okay, let's set up the tree diagram. We are going to do either they're strong enough or they're not strong enough. Okay, and the scenario says she has 25 students to pick from. So that means we have a total of 25, but only 19 of them are strong enough. So this one's a little bit tricky because you have to know that the total is 25. And then how much is left over? 6 are left over that have to be not strong enough. All right, so now this is different because we have a dependent scenario. We cannot just copy and paste the probabilities. The tree diagram is the same because you still are going to have 2 types of students that you can choose from, the strong enough and the not strong enough. But you have to think about, you already picked one of the students in the first scenario, right? So if you go down this path, you already took one of the strong students out. And so that means there's only 18 strong students left out of a total of 24. So this is why it's dependent. And then again, if you picked one of the strong students out first, one of the students is gone, but you didn't pick one of the not strong enough students, so that's the same amount. Okay, the next one, we say again, then you picked one of the not strong enough students first, and so that means you have one less student who's not strong enough out of a total of 24 now. You took one student out. And then if you picked one of the students that wasn't strong enough, then that means you still have all your students that were strong enough. Pro tip, these two numbers need to add up to the denominator, right? You have to add up to 100%. So 9 and 5 makes 19 and 5 makes 24, and 6 and 18 makes 24. That's a good way to double check that you have everything correct. Okay, so again, we could go through, and this one wouldn't take as long. We could go through and say this is the probability of strong enough. And I'm going to move everything over to the left here, make it a little smaller to fit. That would be, and we look to the branches to find the probabilities, the 18 over the 24, and then we would go to our calculator, and this is a scenario where you need to use the fractions. So definitely important that you know how to use your probability or your fraction button on your calculator. So this would be, going back, 19 over 25 times, we need another fraction here, and then this would be 18 out of 24. Notice how the denominator went down once. If I said picking 3 students, then it would go down again, and the next denominator would be 23. So remember that in the dependent situation, the denominator always goes down by 1. And here we're getting 57%. Okay, something to be aware of is that although the denominator always goes down by 1, the numerator does not always go down by 1, because in this scenario, you're saying strong enough, not strong enough. You're going from 19 to 6, right? So it's just important that you know the difference, that sometimes the denominator always goes down by 1, but the numerator sometimes does not. And so this would be 19%. Okay, we don't need to go through and do all of the scenarios here. Let's list the sample space. That's a pretty simple thing to do. We just have strong enough, and then not strong enough, strong enough, and then not and not. Those are our 4 things that could possibly happen as outcomes. Okay, so let's take a look at the questions. She picks 2 students that can carry the supplies. So immediately 2 fractions, right? And then immediately, I know my total is 25, and so I'm just gonna set up my denominators like that. Really, really good strategy. Just set up your denominators right away if it's dependent. And then I'm gonna label here. So it says this one is can. So this is strong enough. And we already did this one. It was 1918. And so that one was 57%, I believe, right? Yeah. Okay, let's take a look at the next one. It says the probability that the first person is strong enough, but the second person is not. We're gonna set up our denominator right away. And that's the one that we just did, where it's this one is strong enough. And then since we picked somebody who was already strong enough, then there's 6 not strong enough people still left. So those guys are still there, and we already did this one. It was 19%. Okay, moving on. We're going to see all 4 of the scenarios, I have a feeling. Picks 2 students that can't carry the supplies. So this is N. We know it's 25, 24. Because the total starts at 25, you take 1 out, it goes down to 24. And then we would do 19, can't, so that would be 6 and 5. So we haven't seen this one before. Let's go ahead and do it. Remember that if you are multiplying in a row, I could put 6, 5, but it doesn't matter, right? Because multiplication is communicative. So try it the other way. You should get the same answer, 5%. So the first student can't, but the second student can is the second one. And so we have 25, 24, and this is the final thing. Not strong enough is 6. That means all 19 of the strong enough students are still there waiting to be picked so that they can help carry the supplies. And so this would be the same percentage, again, because it doesn't matter which one you multiply first. Multiplication, you could do it in either order, so it's also going to be 19%. All right, go ahead and go on to the next question. Give it a shot. This situation is different because she needs to have 3 students. That means there's going to be an extra column. So go ahead and pause, try the next one on your own, and then I will reveal the answers. Okay, yikes, right? This one got really complicated really quick, but it's really, really good practice for you. So go ahead and review the answers here and make sure they make sense to you. Again, feel free anytime that you want to email me with questions. I really appreciate it when you take screenshots of what you're asking about. It makes it a lot easier for me to find your problem and then also look at your work and try to figure out where your mistake was maybe. Yeah, so good luck this week. I know this was really long. Hopefully it was just like a lot of extra explanation and it wasn't something that really gave you a lot of anxiety, because these are really cool and interesting diagrams. Also can be an opportunity to play with colors, play with organization. Yeah, so good luck this week. Keep communicating. You guys are doing great. Sending me emails. I want more and more and more. As many as you can send me, I will take and I will answer. Okay, bye.